Who's ready for the most boring topic all quarter? Yeah, I know. I'll try not to fall asleep while I teach it to you. So this is called IUPAC nomenclature. IUPAC stands for the International Union of Pure and Applied Chemistry or something along those lines. What IUPAC nomenclature is an extraordinarily long set of extremely arbitrary rules which do serve a purpose, and their purpose is that if you properly give something a name based on the IUPAC rules, that name will unambiguously give you one single structure. There will be no confusion as to whether or not the atoms are attached this way or oriented in a certain way. A full correct IUPAC name will ensure that it leads to one and only one structure and will not be ambiguous. Okay, back in business. So again, that leads to a really long set of very boring rules, and I don't test you on IUPAC, so I won't give you a structure and ask you to come up with the IUPAC name, and I will not give you an IUPAC name and ask you to come up with the structure, because I just don't think it's the most important part of organic chemistry. But what I do want to do is go through just enough rules that when you hear certain terms, you know enough to recognize what that name is telling you and what that structure is. And I find that it's a lot easier to take a name and put together a structure than it is to take a structure and figure out what all the rules in terms of which direction I number and how you call this and how you call that. That's a lot more difficult. In your book will oftentimes give you problems in a very annoying way where they'll be like, what happens when you react to iodopropane with what's the product going to be? It's like, why they would do that, I don't know. It's very annoying. I think I'll be able to give you enough nomenclature for you to be able to look at the name and draw it out without too much trouble. If you can't, just Google it and be done with it. Don't sit there and struggle with the IUPAC name, okay? Google is your friend. So let's start with some basic nomenclature, though, just so you can recognize a lot of what you'll be seeing. So we name things based on the number of carbons that are in the chain, and then we're going to have a lot of other rules as well. I feel like I just remembered that I skipped something up here. Yeah, let's just go over this really quickly. So the term hydrocarbon is a carbon that is made of only carbons and hydrogens, so that's sort of a term that encompasses anything with just carbons and hydrogens. More specifically, a hydrocarbon can be defined as an alkane, alkene, alkyne, or arene. So an alkane is considered to be a saturated hydrocarbon. That term saturated just means that there's the maximum number of carbon-hydrogen bonds. And how do you get to the most carbon-hydrogen bonds? You do so by not having any double bonds. Because if you make a double bond between two carbons, it means each carbon has to have one less hydrogen so that it doesn't go over its octet. So that's what's meant by saturated, the maximum number of hydrogens to each carbon, which just simply means that there are no pi bonds, or rings for that matter. An alkene is considered to be unsaturated, and specifically because it has a double bond. And so if it's got a double bond, then it doesn't have the maximum number of hydrogens, so it's considered to be unsaturated. An alkyne is another version of an unsaturated hydrocarbon. So an alkene is specifically a double bond. Doesn't have to be this exact structure. An alkyne is something that is likewise unsaturated, but it has to have a triple bond. And so you could also see things where you have a structure with like more than one alkene, like one over here on this part of the chain and one over here. And those can be referred to as dienes or trienes, depending on how many you have. I don't think you need to worry about that at the moment, but if you see something like that, that's what it's referring to. Okay, and then there's arene. The most common arene that you're going to see in this class is benzene, which is exactly a 6-carbon ring with exactly 3 double bonds, no fewer. It's got to have all 3 double bonds for it to be that. The significance, you'll learn a lot more about benzene rings and these aromatic arene rings in general in 30C and the reactions that they undergo. they react much differently than just normal pi bonded things do. So I'll make sure we address that when we actually get there. But for now, let's consider an arene to be exclusively this compound here. It could have groups coming off of it. You could have an alkyl chain that would still make it an arene, or at least have an arene portion. But for the purposes of this class, let's assume it's that basic structure, which could have additional groups on it. Okay, so nomenclature. So how we name just linear hydrocarbons that don't have any double bonds is what we do is we look at the total number of carbons. So if it's a 1-carbon chain, it's methane, 2-carbon chain, ethane, propane, butane, pentane, and so on. So I don't think you really need to memorize these, and I think up to octane is probably just something people would inherently recognize, probably even up to nonane, probably decane as well, for that matter. They go farther and farther and farther, but longer than that is usually not going to be super important. But again, these are just based on the number of carbons that are in the formula. So if they're all in a straight chain, just based on the number of carbons, methane, ethane, propane, butane, and so on. Let's go down to the next part of IUPAC nomenclature. So now that we just talked about the differences between alkane, alkene, and alkyne, we can take this and cut it up into a prefix and a suffix. So technically, the ones we just named already had a prefix and a suffix. The prefix was for 1-carbon meth, and because it was a saturated hydrocarbon, we gave it the suffix ane. So that's where we got methane, ethane, propane, butane, and so on. We can change that suffix if we have an alkene or an alkyne in the structure. Say ethene or ethine or something like that. So then the suffix instead of ane becomes either ene for alkene or yne for alkyne. See, this is boring, isn't it? It's horrible. Okay, so let's take a look at a couple of these then. The first 3 here will be pretty easy because we're just counting carbons. 1, 2, 3, 4, 5, 6. So that's hexane. 1, 2, 3, 4, 5, so that's pentane. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's dodecane, sorry, not dodecane, just a decane. And then let's modify, or just come up with a new structure and name this one. So now we'll do something that has a different suffix. All right, let's look at this top one first. How many carbons do we have? 4. So our prefix is but. And we have an alkene, not just alkane. So our suffix should be ene. So that would be butene. And here's the beauty, but also the annoying part about IUPAC, is that name isn't specific enough. What's missing from that? Yeah, where's the double bond? Because I could have had a 4-carbon structure with a double bond in the middle, and that would still have, as part of its name, butene. But that's what's good about IUPAC, is it has a set of rules that makes sure we can know which one we're looking at. So what you do is you number your chain in the direction that gives you the lowest possible numbering. So if I numbered it over here as 1, 2, 3, I wouldn't hit my alkene until 3. But clearly, if I number it from the left side first, I hit it immediately at 1. So I only have to give the first location where the alkene starts because, of course, it's connected to the next carbon by way of that double bond. So this would be 1-butene. This one up here would be 2-butene. And when we get to stereochemistry, we'll learn that that name is actually not complete as well. But we're not going to worry about that name right now. Okay, let's take a look at the one on the bottom. How many total carbons? Good, 6 carbons. I think that can be a little confusing with alkynes. Notice how alkynes, I'm drawing the bonds off linearly. It's not exactly a rule that you have to draw it perfectly geometrically accurate, but I think it could lead to confusion in the future, so I like to make sure those are drawn out linearly. So I have one, well, why don't you just tell me? It's a 6-carbon chain, so we know that our prefix is hex. 1, 2, 3, 4, 5, 6, just want to double check. Prefix is hex. And our suffix is now going to be -ine because we have an alkyne. So I'll start by writing hexyne. And then what do I want to give as far as the number? Yeah, good. I want to give it 2. So I want you to get used to not automatically assuming things should be numbered in the more intuitive way of left to right. What we want to do is give the lowest overall number in for when we first hit that double or triple bond. If I were to number this way, 1, 2, 3, 4, I hit it at 4. If I start numbering this way, I would first hit it at 2. So the correct way based on IUPAC would be the numbering that I started on the bottom. 1, 2, 3, 4, 5, 6. So this would be 2 hexyne. And again, I don't have to give the location of both sides of the triple bond because I know that if I give the location where it first starts, it has to move outward from there, so it would be redundant to give another number. Okay, so probably the last important thing to know about nomenclature is how to name things that aren't completely linear. You'll notice that every single structure that we've looked at so far, whether they had double bonds, single bonds, whatever they were, whatever the chain length was, all the carbons were attached one after the other. There was no carbon that had more than one carbon branched off of it. So when we have a carbon chain that has branches coming off of it, we consider those to be substituted carbon chains, and the groups that are those that are substituted are called substituents. So the way we name these is step 1, we name the parent chain by looking at the longest continuous carbon chain. Then we can name the substituents and give their location. So with this first structure here on the top left, what is the longest continuous carbon chain? How many? 4. And you could do 1, 2, 3, 4. I know that's not the intuitive way people would do it, but there's nothing wrong with that. Or you could do it the way people would probably more obviously do it, which is this. It won't give a different name. If you have 2 equally length chains, you're going to end up with the same name regardless of how you sort of highlighted it like I did here. Okay, so do I want to number this one as 1 or this one as 1? The one on the right or the left? Yeah, so I want to number the one on the right as 1 because looking at that, it's going to allow me to hit the substituent I have on there first. So just like with the alkenes and the alkynes where we want to give them the lowest possible number, if I number from the left, it's going to end up at position 3. But if I number 1 from the right, it'll end up at position 2. And that's just the arbitrary rule because there's a whole lot of them. And there's a lot more that I'm going to go through. That I'm not going to go through. So we want to number 1, 2, 3, 4. And I specifically set it up like this because I want you to get used to the fact that you don't, again, always have to consider things from left to right or straight up and straight down. They can go around in circles just as long as you give it the lowest overall numbering and find the longest chain. So the way that we name substituents is we use the same prefix as we did for the parent name. It's 1 carbon, so it would be meth. And the suffix for a substituent is going to be YL, so methyl, ethyl, propyl, butyl, and so on. So the parent name for this is butane. The substituent is methyl, and I have to give its location, which is 2. So this is 2-methyl. I'm just going to redraw this out so you can see it properly. 2-methyl, no space, butane. So a couple of the rules, I don't want to go through these by just like reading everything you see up here, but whenever you have a number next to a letter, they're separated by a dash, so 2-methyl. Whenever you name substituents, your very last substituent that's included in the name should be one word with the parent name. So it's not 2-methyl space butane, it's 2-methyl butane, all one word. If you have multiple numbers, which we haven't seen an example of yet, but we will in just a second, if you have multiple numbers that are next to one another, those are separated by commas. So numbers are separated by commas, numbers and letters are separated by dashes. And letters would also be separated by dashes. Okay, so let's take a look at this one. This is a good example. What is our longest continuous carbon chain for this top right? Good, 6. So there's multiple different ways we could do this, and we would get the same name. Intuitively, most people would probably do it like this. But just to add a little spice here to IUPAC, I'm going to do it this way. It's going to give me the exact same name. Right? Obviously, most people would probably just do it zigzag left to right, but it's not going to give me a different answer. Okay, so now let's look at our substituents. We have a methyl, and a methyl. They're not at the same location. If I have multiple of the same substituent, like more than one ethyl group, or more than one propyl group, or more than one butyl group, even if they're not at the same position or different positions, we're going to take however many we have and add a prefix in addition to that of di, tri, tetra, etc. So here there are two methyl groups, even though they're at different positions, so we're going to call that dimethyl when it comes to labeling the substituents. So let's start with the parent name. We've got hexane, and then we'll put it all together. We have two methyl groups, so we have a dimethyl. And then we have to give the locations of the methyls. So what are those locations? What are the numbers? Good. Again, don't just inherently number from left to right. We want to number 1, 2, 3, 4, 5, 6. Because if we numbered the other way, we would hit 1, 2, 3, 4. We wouldn't hit the first methyl group until the number 4. This way, we hit the first methyl group at 2. Okay, so let's put this all together then. So now we want to give both locations. The locations are 2 and 3. This is an example of numbers being next to each other, so we'll separate them by commas. 2, 3. Now I'm about to separate a number from a letter, so dash, dimethyl, and then the parent name gets tacked right onto the end without a space. 2,3-dimethyl hexane. Okay, so I want to do one more just in terms of finding the longest continuous chain. So what is our longest continuous chain here? Yeah, good. Don't let your brain trick you. It doesn't have to go like this. So the longest continuous chain, 1, 2, 3, 4, 5, 6, 7. Right, so make sure you consider any possible pathway. And the longest chain we're going to get here is going to be 7. And it would have been fine if I had started with this methyl. It's going to make it even less intuitive looking. I'm still going to get that 7-carbon chain. And again, the name is not going to change as a result. Okay. So 1, 2, 3, 4, 5, 6, 7. So our parent name is therefore going to be heptane. And then we have a substituent here and a substituent here. So which end are we going to number on, A or B? A, again, yeah, we're concerned about where we hit the very first substituent with the lowest number. So we're going to start numbering from the side I have labeled A. So that will be 1, 2, 3, 4, 5, 6, 7. So we would have 2-methyl. And then here's where it gets tricky. If your substituent itself is branched, then you have to apply IUPAC rules to that, which is really, really, really annoying. So by IUPAC rules, you would then give it this substituent its own set of subnumbers. And you would give number 1 to the direct point of attachment, which would be here. Then you would number out to the longest continuous chain, which here either methyl is going to give the same chain length, so pick one. And then you would have to sort of give this a sub-substituent name. And honestly, I'm not even going to bother going through it because it's very, very annoying. We've come up with sort of a hybrid way of naming things by using what are referred to as common names. There are common names for a lot of molecules and also for just substituents or groups that were used before the IUPAC system was put into place. And when you have a 3-carbon chain that's branched like this, exactly what you see here, that's called isopropyl. It really just meant that it's not a normal linear propyl chain, but an isomer of it. So the generic name for that or common name is isopropyl. I like to point out these common names when they're things that you're going to hear over and over and over again, and I want you to be able to recognize immediately. It's not because I'm going to have an exam question that says draw an isopropyl group or draw a tert-butyl group. It's because you're going to hear me say it all the time. You're going to want to know what I mean when I say that. So this is isopropyl. This one is called tert-butyl. We'll see that one a lot. This is sec-butyl. You're not going to see that often. I really want to highlight the times when you're gonna hear a term pretty often. So I would cheat here and call this 2-methyl 4-isopropyl heptane. One thing you have to keep in mind, not really, but I'll say it anyway, is that you're supposed to list the substituents in alphabetical order, not in the numerical order that they come in. And then there's rules as to whether or not the iso prefix is considered in that alphabetical order, and honestly, I don't even remember without looking up the rule if it is. So it might be 2-methyl 4-isopropyl, or if I'm wrong about the prefix, then it would be 4-isopropyl 2-methyl when you list the groups. But again, those kinds of things are ambiguities that you could mess up if you had the structure and were coming up with a name. But if you have the name, it's not really that hard to just put things at the right number. And so I think a lot of times when you look at the names in your book, you'll be able to come up with these structures pretty easily. And if you can't, Google. So I'm not even going to do the full IUPAC name for that one there. It's pretty annoying. One last thing that I just want to mention is that we can also break this up into something called a prefix, infix, and suffix, where we're basically combining the same prefixes we did before, meth, eth, prop, and so on. Then we consider whether it's an alkane, alkene, alkyne as an infix. And the infix for alkene would just be the an without the e. For ene would be the en without the additional e. For the ine would be the yn. Basically, you drop the e from all of them. And then your suffix comes from a functional group, right? Because so far we've just looked at things with carbons and hydrogens. So if we looked at something like this, we've got 1, 2, 3, 4 carbons. There's no double bonds. So we have but as our prefix. Instead of ane for butane, just the an part, we drop the e for when we have a functional group. And then we have an alcohol, and the suffix for that is ol. So this would be butanol. What am I missing, though? I'm missing the location of the alcohol, because if I drew this, that's a 4-carbon chain. It's all alkane, and it's got an alcohol. So that also includes butanol in the name. So we need a location now for that alcohol. So we do a similar thing. We give the functional group the lowest possible number. And so what I have here is not correct. 1, 2, 3, 4. I would call this one 1-butanol. Here, 1, 2, 3, 4. I would call this one 2-butanol. And actually here, again, when we get into stereochemistry, we'll find out that even that name is not fully complete, but we do not need to worry about that now. So now just for fun, imagine this gets even more complex. I have the suffixes here for all these different functional groups. So this one, let's see, 1, 2, 3, 4, 5, 6 is 6 carbons. So this would be hex, an for alkane, and then I would add this oic acid. Hexanoic acid, and there is actually a space as shown. If I had a 6-carbon chain with an amine, it would be hexanamine. And so we have all of these that we can put together. But now imagine, just for fun, that we have 3 different functional groups. They can't all be part of the parent name. So then there's a whole set of rules about which functional groups should be prioritized in the parent name and which should be named as substituents instead. And if you have an alcohol that's named as a substituent rather than part of the parent name, it no longer is denoted by OL. We're not going to do that. It sounds even worse than what we've gone through so far. I think we can all agree. But it gets complicated, trust me. Okay, so the very last thing we're going to talk about in nomenclature is just cyclic structures. For the most part, I'm not going to go through all these rules. If you like these nice rules and putting together and having a computer brain, by all means, read through these, go onto the IUPAC website, dig in, have a blast. I'm not at all entertained by this, but I just want to show you how we deal with cyclic structures. So we're going to take the same parent name. So this one, the longest continuous chain is 6. It's in a ring. So I just add cyclo to the front. So this is cyclohexane, and it's got a substituent, which is a methyl. So this is methyl cyclohexane. When you only have one substituent, it's redundant to put a number. You could call it 1, 2, 3, 4. We could call it anything you want, but it wouldn't be the correct IUPAC term. When there's only one group on the ring, you just don't include a number because all the positions are equal, so it doesn't matter where it is. I'm not going to bother with the rules of what you do when you have something that's di-substituted or tri-substituted, because again, if you read the name, you'll be able to come up with the structure. But if you have to go through all the rules to figure out the exact right way to number it, you won't necessarily, your name could be wrong and it would still give someone the right structure, right? So to me, that's just not super important. Okay, so what's important is what we're about to cover next, which is conformations of alkanes and cycloalkanes. And I know we're not going to get very far on this, but if I draw a structure like this and one like this, are these the same? Are they the same compound? They're the same compound. They look different. Something's different about it, but they're the same compound. It's a 4-carbon chain with the exact same number of hydrogens. Ultimately, what this is amounts to a rotation about this sigma bond. If I imagine grabbing onto this methyl down here and pulling it down, rotating about that bond in the middle, I would get to the one on the right. And there's a more convenient way to look at